Hello, you're welcome to our class today once again. In this class today, we are going to be looking at the a summary of the laws of indices. Remember, we are connecting indices to the theory of logarithm, indices and the theory of logarithm. That is actually what we are going to be looking at. Um, Now, I want to exactly look at the laws of indices in a breakdown. Okay, the laws of indices starting from the first one, to the maybe the last one. So I implore you to be part of this class so that you can see the applications of these laws in the classes we have had. Okay, because yes, we have applied the laws of indices in so many classes, okay, in solving issues, problems that has to do with indices, indical equations, indices that has equations, and then clearing roots, clearing powers, and all that. So what I exactly want to do right away is to show us a summary of those laws that we have used. So I'm trusting God that we are going to, even as I'm going to be looking at this right now, I'm going to also be doing some little drafting, touches that can help us to buttress, the laws of indices as we have applied them. Okay, so if you come to the laws of indices, this may not be the first time you are coming across something that says, number one, if you have a raised to power x multiplying a raised to power y, that it will be a raised to power x plus y, meaning when we are, indices is coming from that word index. Index, meaning that if I write 8, this is a number, I can rewrite this in its index form. That is, this is the same thing as 2 raised to power 3. Okay, so this is now the base, and this is the index upon which this base is raised. So now, multiplication, division, and other activities we do that has to do with terms that are in their index form, that is what we call indices. Do you get it now? That's what we call indices. So now, if you look at this, you see a term we have already represented in algebraic form as a raised to power x, multiplying another term as a raised to power y. So, and we are saying that when you have something like this, that you can add their powers. Do we have a proof for that? Let's see whether we can make a proof for it. All right. Now, if I have, take for instance, I have used here. What about if I have 8 times 8? And you know that 8 times 8 is 64. Okay. Is there any way I can also show you passing through this to show you that this is consistent? Now, I can write this 8 now as 2 raised to power 3, then multiplying 2 raised to power 3 again. And if I do what is said here, I am going to be having 2 raised to power 3 plus 3, which is 2 raised to power 6. Now, question, is 2 raised to power 6 64? Yes, you can check it out in your calculator. That 2 raised to power 6, that is 2 times 2 times 2 times 2 into 6 places will give you 64. It then means that this is true for this, that anytime I have numbers that are being multiplied and they are in their index form, that I can add their powers and it will give me the same result as when those numbers are multiplied. I'm sure that is very elaborate. Okay, what about the second law that says if you have this a raised to power x being divided by a raised to power y, that what you quickly do is to subtract their powers. Okay, so we take it like this. a raised to power x minus y. Remember the one that is dividing this. That's the power that you take away to the best of that explanation. Do we get that? Okay. So how can we explain this? So if I have something like 32 divided by 4, which you know is 8, can I pass through this again to show it? Let me try and see. 32 is what? Is 2 raised to power 5 in index form. And 4, you know, is 2 raised to power 2 in index form. And this operation now is in index form. So, and let's try and see whether if we do what this says, whether the result we obtain here will be consistent with what we're going to get. So, we take it like this: 2 raised to power 5 minus 2, which will give us 2 raised to power 3. Question: 2 raised to power 3, is it 8? Yes, 2 raised to power 3 is what? Is 8. Is 8. So it then means that anytime I have an expression like this that is in index form, I can subtract their powers and get a consistent value. Do we get that? Okay. The third one, if we have something like a, now this is division, this is multiplication law, but this one I'm going to give us now, we call it the zero index law. That is, if I have something like a raised to power 0, a raised to power 0, and they said that it is 1, let's see whether we can accept it. Let's see whether we have anything to show that this is consistent. A raised to power 0 is 1. Let me try something like this. I have been working with 8, even numbers. Let me see. Now, if you have 8 divided by 8, what is it? 8 divided by 8 is 1. It's 1. I'm sure that one, there is no argument about it. Okay. Now, can I pass through this as well as I've been saying to show this? Let's see. Now, 8 is the same thing as 2 raised to power 3. And I am saying divided by 2 again, raised to power 3. Now, by this operation, I have already known that I'm going to say 2 raised to power 3 minus 3, which is 2 raised to power what? 0. Wow. Can we bring this together? If this quantity, this 8 over 8, is the same thing as 2 raised to power 0, and 8 over 8 is 1, it then means logically that 2 raised to power 0 is also 1. I'm sure that logic is very, very acceptable. If 8 over 8 is 1, and 8 over 8 gave us 2 raised to power 0, it then means, can we logically conclude that 2 raised to power 0 is also equal to 1? Yes, it's a very, very logical statement that can be concluded in that way. Okay, so this is what we call the zero index law. I'm sure that is very, very clear. What about what we call number 4 now? What about what we call the negative index law? The negative index law. It then means I have now a raised to power minus x. And what does this law say? This law says that any term that is raised to a negative index is equal to the reciprocal of its positive index, is equal to the reciprocal of its positive index. And reciprocal means 1 over something. So it then means I am going to rewrite this as 1 over a raised to power its positive index. Its positive index is x. Its positive index is a raised to power x. Okay, so this is now said to be equals to this. Do you have anything to show for that? Let's try. If I have if I have, maybe I'll come from here again. Maybe I'll come from here again. Let me try this. 1 over 8. 1 over 8. Okay. Now, we have already agreed that any term raised to power 0 is 1. Now, can I rewrite this as 8 now raised to power 0, which you now know is 1 over 8. This is equal to this. You agree with that? Fine. Permit me to rewrite this as 2 raised to power 3 now. Oh, there is something you have to agree with me here. That this 3 will multiply this 0. We are coming down to that now in the next law. It is called product power law. So this 3 will multiply this. Okay. Let me put equals to here. All over this is 2 raised to power what? 3. Now this is division. I'm sure you can see that. Now you can write this as, 3 times 0 is 0. So you can write this as 2 now. 2 raised to power 0 divided by 2 raised to power 3. Now, what do you have now? Let's subtract their powers. You are going to have 2 raised to power 0 minus 3. What do you achieve? You have 2 now raised to power minus 3. Can you see that? 2 raised to power minus 3. 2 raised to power minus 3. Wow. 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 Can I write this 1 over 8? Can I write this 1 over 8 as 1 over 2 to power 3? I'm sure you accept that one. Then if this thing is what brought me here, and this same thing is what landed me here, it then means that these two things, they have a connection. That is to say that this one, which is 2 raised to power, this one, which is 2 raised to power minus 3, will be the same thing as 1 over 2 raised to power 3. No argument about it. So we have comfortably been able to show that anytime you have a raised to power minus, anytime you have a term that is raised to the power that is negative, it is equal to the reciprocal of its positive index. It is very, very clear. It is very, very clear. So you can see this, that the explanation is very, very clear. I don't think there's any argument, except if you have something else. I don't think there is. So let's look at the fifth one. Now, this first 51 is called the square root law. The square root law. And what does it say? It says that when you have a raised to power 1 over 2, that it is equals to square root of a. Good. Do we have anything to show for it? Let's see. If I've been using these even numbers. If I have 4 to power 1 over 2, wonderful. And I am supposed to do what they did here, what they said here, that I should write square root of 4, and that will give me, of course, 2. Is there anything I have to? Is it how will I? Yes, how will I connect this half and this, and it is this? Let me try other way around, which I am a little bit comfortable with, or I can say a little bit, I can say for certainty that this is appropriate. Can I write 4 as 2 raised to power 2? Yes. And there is existing power there, which is half. And by product power law, which I said I am coming to show you, is going to multiply the really existing power, which is 1 over 2. So, 2 times half is 1. So, do we have 2 raised to power 1? Yes. And the answer is what? Wow. So this, anytime I see a term raised to power half, I should take the square root of that term, because I have seen that this 4 raised to power half gave me, by this operation, gave me 2, and it's equivalent to the square root of 4. So this is verified. If you also like, we can still look at something. Excuse me. We can still look at something to show whether that makes some sense. Okay, let's look at something like this, like 20 20 is it 27 I'm going to use now. Let me use 9. If I say 9 raised to power half, and this 9 I know is 3 raised to power 2, and it's going to multiply that existing 1 over 2, this will become 3 raised to power 1, and is equals to 3. And this 3 I'm seeing here is the square root of 9. So it then means that if I have 9 raised to power half, I can quickly say let it be square root of 9, and it will give me 3. So I think that is, acceptable. That is acceptable. Okay. The next thing we are going to look at is that product power law, which I mentioned there. That product power law. That should be number 6. Now, product power law, what does it say? The product power law says if you have A that has an index X, but this is raised to another index. This is an index raised to another index Y. That what you should do is to take the product of the powers. That is to say, A will become raised to power X times Y, which is A raised to power X Y. Do you see that? So, how can I be able to verify that this is true? I'll choose a number. If you have, you know that 8 raised to power 2 is 64. I don't think you have argument about that. Otherwise, you press your calculator there and get it. 8 raised to power 2 is 64. Now, you know that this 8 is 2 raised to power 3. And let's try and see, because there's an existing power there, which is this. Let's try and see whether the product of this and this will give us this. So I am going to have 2 raised to power 3 times 2. And that will give me 2 raised to power 6. This 2 raised to power 6, is it 64? Yes, it is 64. If that is true, it then means that this statement is consistent. The statement is true. So anytime I have a term in index raised to another index, I should just, as easy as possible, take the product of the powers, and it will be equivalent to whatever value I could have got when we have the number in maybe in this form. Okay. Which one are we going to look at again now? Finally, I think the 7 to 1. The 7 to 1. So now I am bringing the summary of all these um, laws of indices. If you check out the introduction to, is it introduction to indices? About 5 classes we've had already on indices. Okay, so we were applying these laws, applying them. Please, this is not the beginning of this class. I brought this at the end of the class almost, even though we are still going to have other classes. If I discover problems, I'll bring them up. I'll keep on updating the classes we have had. Okay, I'll keep on bringing problems. Okay, so that is that. What I'm saying in essence is that you check out those classes to see how we have been applying all this, about 7 of them now. The 7th one is what I want to give. Okay, check out those classes so that you can be able to see all the applications in solving real life problems, indical equations, and all that. Okay. what do we have here now? The seventh one. We've taken a look at this. Let's take a look at what I call nth root law. Nth root law. What does this law say? You realize that you have accepted that, let me just state it. It says a raised to power a over b is equals to bnth root of a. Sorry, I have to change this variable here. No, cannot be written like this. Okay, let me use a raised to power x. Okay, or let me use a raised to power b over x. I think that's better. So if you separate this, you are going to be seeing a. Please follow me. If you separate this, you are going to be seeing a raised to power 1 over x multiplying b. And permit me now, you noticed what happened between here and when we are looking at here. Okay, I'm sure you noticed what happened there. So that this raised to power this is square root of that. So this now will be the x root, because that is 2 and we're taking square root. Okay, we will have x root of what? A. Then all raised to power b. All raised to power b. Yes, because 27, take for instance, if I have 27 raised to power 1 over 3, and I do what I did over there, no, I am going to have 27 is the same thing as 3 raised to power 3. Then you know that 3 raised to power 3 is going to multiply 1 over 3, which is already existing. And then this cancel this will give us 3 raised to power 1, which is 20. Sorry, 3 raised to power 1. What am I writing? Which is equals to 3. Okay. Now, if this 27 raised to power 1 over 3 gave us 3, can you check in your calculator the cube root of 3? Just check that. Cube root of 3. That's what I mean is this. Cube root of 3. Not 3. Sorry. Cube root of 27. Can you check what it will give? Cube root of 27. It will give you 3. So it then means that 27 raised to power 1 over 3 is 3. And if I take cube root of 27 and it gives me 3, then if you come here, you will conclude with me or accept what I'm going to tell you, that when you have a raised to power 1 over x that is equals to x root of a, you can also verify. Let's try another one again, like 81 raised to power 1 over 4. Now you know that 81 is the same thing as 3 raised to power 4. Now this will multiply the existing power, which is 1 over 4. You see that this will become 3 raised to power 1, which is 3. So what am I trying to do? I'm trying to bring us to a conclusion that when you have a raised power, raised power 1 over x, that is the x root of a. Okay. And if you have now, like I am going to show now, still to buttress what I am saying, if you have excuse me, if you now have something like this, a raised to power b over x, that is going to be a raised to power. If you can see what I did here, then we can now be able to take the x root of a, then raise it to power b. Take for instance, let me show you something here. In this example I have here, let me show you something. Now, I have solved this problem in the previous classes already, but I am going to just take a portion of it to buttress what I am saying here, just a portion of it. You can visit that class and check other explanations and some other questions that were solved inside that same place. I have something like x plus 3, and then it is raised to power 4 over 3, and it is equated to 16. And I want to apply the law of indices in handling this, and obviously what I have just explained here. Now, how is it going to go? How is it going to go? You now realize that if I come here, I can choose to have x plus 3, and then separate these powers, and I will have 1 over 3, then multiplying 4. Okay, then equals to, this side is 2 raised to power 4, so that's 16. So did you notice what I'm doing here, what I said here now on that place? So if you realize this, you now see that this will be third root, or you can say the cube root. Okay, the cube root of x plus 3, and then raised to power 4 equals to 2 raised to power 4. Now, by law of indices, since the powers are the same, I can equate the powers. Now, my concern is not driving this down. My concern is the application of this knowledge in handling a problem like this. That's my concern. So, but let me just bring it down so that you can just be part of what we are discussing. So, finally, I say since the powers are equal, equate the base, and we're going to have the cube root of x plus 3. I'm sure I have not made this class to be too lengthy, equals to 2. So now the only way to remove this cube root now is to take this root now is to raise this to power 3, both sides. Okay, so taking the third root of both sides, I can have 3. This is root x plus 3, then raise it to power 3, equate it to 2, and also raise this one to power 3. I have not committed any offense. What I did to the right hand side, I did to the left hand side. So what I have here is just x plus 3 equals to, this is 8. Now here I have x equals to 8 minus, I'm not a left-handed person, sorry. This is 8 minus 3. So at the end of the day, I now have x equals to 5. I said my concern is not bringing you down here. My concern is the application of this knowledge in handling a problem like this. Please, this is the summary of the laws of indices. This is the summary of it, and we have been able to track it down from the first rule down to all these rules. Please check the classes you have had, about 5 classes down there, okay, in the list down there. Okay, we have been able to apply all these rules in solving practical problems. And if you now look at this summary and then begin to follow those classes one after the other, you see the applications of all these. We've not exhausted the problems, the questions we have. We are still going to continue. But I intended to bring this as a summary part of what we are doing so that you can now be able to see how we are capturing it in all the examples we have solved already. Thank you so much for being part of the class. Please share to your friends out there. Click on the subscription button to subscribe and like our video. and then be a part of encouragement to us as we are making our impact in the society. God bless you.